Hello geometers, and welcome back to another video lesson with Mr. Forster. Your asynchronous tasks for today are to work through the notes on triangle congruence using side-side-side and side-angle-side relationships. And then your assignment is going to be posted with this in Google Classroom, and it will be another Kami assignment that you'll be filling out or printing off and uploading photos of. So let's go ahead and get started. A couple of things to note is our first shortcut for proving triangles to be congruent is this thing called the side-side-side congruence theorem. So we talked a little bit yesterday in class, and we might even have talked about it a little bit today in class about the idea that in order to prove two figures to be congruent, I need to know all of their measurements are equal. That's not entirely true because we have some shortcuts that allow us to jump to that conclusion. And our first one is this side-side-side congruence theorem. So what this states is that if I know that three sides of one triangle are congruent to the three sides of another triangle, then the two triangles will inherently be congruent. So the congruent statement I would make for these two triangles is that triangle GHF is congruent to triangle PQR. And just a reminder, the order on that statement does matter. Let's see what this would look like in action in a proof format. So again, we'll have some statements and some reasons. For the given, the item that is given to me is that the point H is the midpoint of the segment GK, and HF is congruent to HJ, and FG is congruent to JK. So some of the congruence pieces are marked on the diagram, so you can see the red tick marks on FH and HJ, as well as the double dashes on FG and JK. And my goal is to prove that these two triangles are in fact congruent triangles. So the first thing that I'm going to do, much like we've done in the past, is I'm going to relist the given information, and the reason that I can do that is it is given to me. The second thing that I'm going to do is I'm going to focus on the fact that this is the midpoint. So H is the midpoint of GK, so that means that H here splits this entire segment into two equal lengths, which means that GH is congruent to HK. That's what a midpoint does. So this being in the middle means that this segment is equal to this segment's length. And the reason for that is exactly what it means to be a midpoint. So since H is the midpoint, then we can use that definition of what a midpoint does. And so finally, now I have all three sides are congruent, which means I can claim that the triangles are congruent, and my justification is that all three sides are congruent. So I would use the SSS, or side-side-side congruence theorem. Another example of a side-side-side proof here that we might see. This time we're given that AB is congruent to CB, and that AD is congruent to CD here. So much like before, I'm going to state my given arguments, and the reason for that is that they are given to me. And then I talked about this in our previous video, but we have this shared side length going from B to D that is used by both triangles, and whenever I see this is something that I can use to say that, well, this length is going to be the same for both triangles. So BD is congruent to itself. We call this formally the reflexive property, and then for our class, you can also call it the no-duh property because, well, no-duh, it's the same as itself. It seems silly to have to say it, but it's on our list of things to establish. Now that we have established that all three sides are congruent, now we can make the claim that the two triangles are congruent, and again, our reason for this is the side-side-side congruence theorem. It's not our only shortcut. We have another one that we'll talk about today, as well as a few more in upcoming lessons. If we ever see this scenario where I have what's called side angle side, which formally states that if two sides and an included angle, and we'll talk about what that means here in a second, of one triangle are congruent to two sides and an included angle of another triangle, then the two triangles are congruent. So in this case, we would say triangle BCA is congruent to triangle FDE. This angle in each case, when we talk about the included angle, is the angle that is formed by the two segments that we know are congruent. So it's the angle that's part of that V shape in both triangles. So that's what it means to be an included angle, is the two segments that I know are congruent actually make the angle that I have that is also congruent. Let's look and see if we can explore this a little further. So here we're going to walk through some examples of naming that included angle. So in my first case, I have the pair of segments AB, which is here, and BD, which is here. So those two are marked in orange. And the angle that is formed by that V shape is the angle right there, kind of up in the top left-hand corner by B. And so I have a few ways that I could name this angle. I could go from A to B to D. So if I started at A, went to B, then to D, so I would name an angle ABD. Or if it was a path and I walked from D to B and then down to A, that would be my other option. So again, the two names that I have is angle ABD or angle DBA. The next pair of segments that I have, we'll mark in blue. So I have BC up top, and then I have CD on the right-hand side of that figure. So the included angle in between them, again, is what's formed by those two segments. And in this case, I have two options again. I can go from B to C to D, or I can go from D to C to B. Those would be the two ways that I could name this. There's actually a third way I could name this, and I failed to mention it in the animated version, but I could also call this angle C. So in this case, I could also call this angle C because there's no other segments or anything blocking me from being able to do so. So this one I could also call angle C. Our final example, if I have segment DB, which again is that diagonal segment marked in green there, or BC, which is that top segment there, this time the included angle would be up in that top left-hand corner by B. I can't call it angle B here because, well, I have the orange angle is by B and so is the green angle. So it would be ambiguous of me to try and name it angle B. It wouldn't make sense because I wouldn't know which of these two angles it is. But in this case, I could use like I did before, which is I could say that it would be either DBC or CBD. And again, I think of how I walk along these two segments. So if I go from D up to B and then out to C, that would create that V shape in green. Or if I started at C, walked over to B, and then down to D, that would also create that green V shape as well. Looking at a possible application of our side angle side congruence theorem, I want you to take a moment and pause and see if you can determine whether or not these triangles are congruent. I'll give you a moment to pause the video now. Before I tell you yes or no, one thing that we could claim about these two triangles is that we would have these two angles here would be congruent, and these are called vertical angles. And if we look in triangle BCD over here, that angle is made by the two segments that are marked. So that would be an included angle. However, this angle on the triangle ABE is not made by those two segments. I have my congruent segment here and then my other congruent segment over here, but my angle is not formed by those two. So in this case, we would say no, there's not enough information for us to claim that these two triangles are in fact congruent. So again, I've mentioned this a few times, but it looks like it is never really a good reason or justification. So in this case, the triangles may look congruent, but we don't have enough information to prove without a doubt that they would be. Let's look at an example where we change it a little bit, and we have a similar scenario here. However, I've moved one of the congruence relationships. So in this case, we're given that EB is congruent to CB, AB, that segment is congruent to DB, and our goal is to prove that the two triangles are in fact congruent. A quick note, in your notes, I believe this part is labeled AEB, and so that's a typo. It should say ABE in your notes, so I apologize for that. But if we look at our process here, much like before, we are going to first state our given. And then just like in the example above, I can use the claim that these two angles are congruent by the nature of them being vertical angles. So angle ABE is congruent to angle DBC. And again, a reminder, you can't call them angle B because which one is angle B? This is the question that I would have for you. So we need to use more than just that single letter here because I have multiple segments and multiple angles in that location. Once I have this, we may notice that the angles in both triangles are in fact the included angle. So that means that I have the criteria for side angle side, which means that the two triangles are in fact congruent here. And again, my reason for that is I have two sides are congruent and the included angle between those two sides for both triangles are congruent. That concludes the notes portion for today. You do have a very short homework assignment. Again, just a reminder, there is a homework assignment in Google Classroom attached to this. I believe it is a half page or so. There's a few proofs, and then practicing identifying which of these two congruence theorems you would use given a figure. And there is also the option for neither. So in some cases, we don't have enough information. So keep that in mind as you're working through your homework. I hope you have a fantastic rest of your day, and I look forward to seeing you in class.